Good afternoon, ladies and gentlemen. Welcome to attend the Hong Kong IAS Distinguished Lecture by Professor Chi Hao Chen. I am Kwai Meno, the moderator of today's talk. Professor Chi Hao Chen is a world authority in applied electromagnetics. He received his PhD degree in electrical engineering from the University of Illinois at Urbana-Champaign, USA in 1987. He joined the Department of Electronic Engineering, now Electrical Engineering, City University of Hong Kong as a professor and was promoted to chair professor of electronic engineering in 1998. Elected a fellow of the IEEE in 2002, Professor Chen received the IEEE Antenna and Propagation Society Harrington Mitra Computational Electromagnetics Awards in 2019. He also received the 2019 Distinguished Alumni Award from the Electrical and Computer Engineering Department at UIUC. Without further ado, let's welcome Professor Chi Chen.
Thank you, Professor Lok, for your kind introductions. First of all, I would like to thank Professor Jacob Huang, the Executive Directors of the Hong Kong IAS, for inviting me to give a lectures in this Hong Kong IAS Distinguished Lecture Series on Electronics and Photonics. And I have several hats. I am the director of the State Key Laboratory of Terahertz and Millimeter Waves at City University of Hong Kong. Our laboratory has been funded by the Hong Kong Innovations and Technology Commissions, ITC. And apparently, our funding will be increased in the near future. So for the attendants who are interested in visiting us, and please contact our professors, and then we'll see what we can do. And I have another head as the Director of Talent and Education Development Office. Now for those attendants who have children that who are about to attend universities, they can also send them there, here, and we can have actually scholarships and so on if the grades are good. And I will take good care of them, and that is something that I can promise. Now, I would like to dedicate this lecture to two of my mentors, Professor Raj Mitra, who was my PhD supervisor at Illinois, and he attracted a large number of excellent students and postdocs to join his research group. And many of them are now become research leaders in their own right, and many of them are my longtime friends. Now, although the late Professor Jack Richmond was not my official supervisors for my master's degree, but whenever I had encountered difficulties, I would ask for his advice. Professor Jack Richmond wrote me 3 recommendations. The first one is for the admissions to the research program at UIUC. And the second reference he wrote me is for my first teaching job at the University of Washington. And the third reference he wrote me is for my applications of the U.S. National Science Foundation Presidential Young Investigator Award. Unfortunately, after he wrote me the references, like less than 3 weeks, and he passed away. And I am very fortunate to be able to learn from these world-renowned professors. And in fact, they belong to the first generations of gurus in computational electromagnetics. Now, this is the frequency spectrum for the wireless communications. And you can see that from 4G, 5G, and in the future, 6G. Now, it usually takes a 10-year development cycle for new generations of wireless communications. And it's expected for 6G is expected to be deployed in the year 2030. And for the frequency for 6G communications are basically at the lower attenuation rate of the signal at different tips of this curve. Now, here we can see that there are some salient features of the 6G. For example, the data rate will be extremely high. Let's say expected to be the peak data rate will be larger than 100 gigabit per second. And in terms of the latency, it will be sub-milliseconds. And it will have an extreme massive connectivity. We are talking about maybe 10 million connected devices within 1 square kilometers. Now, another important features of the 6G is the integrations of the air, space, sea, and ground. So everything will be connected in the future. Now, there are other important applications too. For example, here we can see that we can have chip-to-chip connections as well as machine-to-machine connections. Now, this kind of application will be very important in the future for example, in the big data center. Now, another important application will be so-called the holographic telepresence. Maybe in the future, our digital twin can communicate with other people face-to-face, although ourselves and our twin are actually maybe thousands of miles apart. Now, there are other important applications too. For example, for 6G, tactile internet will be important. Okay? For example, if we are having the robot to do the remote surgery, if the doctor on the other side can also sense some of the tactile feeling of the robot, then they can conduct their surgery in a much better situations. Now, at present, the telemedicine for the basically for the Chinese medicine is not too successful in the sense that the doctor cannot sense our pulse remotely. Okay, maybe in the future we can rectify this problem with 6G. Now, here are some of the research activities that have been conducted around the globe. For example, back in 2013, a German group already successfully demonstrated a 100 gigabit transmissions for a distance of 20 meters at the frequency of 237.5 gigahertz. Now, the group led by the University of Southern California in 2014, they have demonstrated 32 gigabit per second link over a 2.5 meter, okay, at only 28 gigahertz, okay, using 4 independent orbital angular momentum OAM beams, okay, for 2 polarizations, the vertical and horizontal polarizations. Now, this approach actually was extended by the NTT group in Japan in 2018. They have demonstrated the speed of 100 gigabit per second. Now, using a different approach, the French group, okay, had also demonstrated a 32 gigabit per second data link at 385 gigahertz for a very short distance of 0.25 meter in 2015. Now, the group extended this to 100 gigabit per second together with Tektronix in 2018. Now, there are other work. For example, the University of Padova group in Italy, they have basically showed the feasibility of satellite communication at 180 gigahertz, provided that the transmitter power is high at 33 dBm, and the antennas need to have an antenna gains of about 50 dBi for the LEO satellite. Now, the Samsung Electronics and UC Santa Barbara has collaborated and demonstrated a 6.2 gigabit per second data rate for a range of 15 meters using 140 gigahertz digital beamforming approach. T.S. Rappaport at the NYU Wireless Center actually showed that the path law through the typical air is only 10 dB per kilometer, around 0.4 terahertz, that is 400 gigahertz, and up to at 900 gigahertz, the attenuation is 100 dB per kilometer. That means if you use a smaller cells, we can actually have the wireless communication using this terahertz frequency. And also last year, LG demonstrated the 6G data transmission outdoor within a range of 100 meters, okay, at 155 to 175 gigahertz, and because they have a very high power amplifier. And Huawei published a 6G white paper also last year, and in fact you can download this white paper on the internet. Now, the Purple Mountain Laboratory achieved a record-breaking wireless transmission speed of 206 gigabit per second using 360 to 430 gigahertz system in January 2022. And this effort was led by Professor You Xiaohu. Okay? And in 2018, the Academy of Finland established an 8-year, 250 million euro 6G flagship program, which is hosted by the University of Oulu. Now, here actually the 6G flagship actually published a white papers back in September 2019. And some of the technology they listed here from low uncertainty to high uncertainty, low impact to high impact. So if we were to consider doing research in terahertz frequencies, so we should be looking at some of this area here. For example, terahertz communications, CMOS in terahertz. For material, they use graphene and lossless materials at terahertz frequencies. Now, so these are some of the 6G targets. For example, 100 gigabit per second to 1 terabit per second peak data rate. And for positioning, for indoor, it will be within 10 centimeter, and for outdoor, 1 meter. And the latency, we have already mentioned it before, sub-millimeter wave, sub-millimeter seconds. And in terms of the density for the devices, it could be 100 devices per cubic meters. So of course, we need to develop a lot of new technology in order to meet this requirement. Now, so here we can see that here are the patent applications for 6G technology, and that was reported in April 2021. And out of this, about 38,000 applications, China actually has 35% of it. Okay? And here it shows the 4 key technologies of the 6G communication, namely the AI-based air interface technology, terahertz technology, AS-based sea-ground integration technology, and the deterministic network technologies. And the blue one is the percentage of the Chinese applications. And as you can see that the largest one is in this area of the air-space sea-ground integration technology with over 25,000 applications. And the China actually has 31% of it. Now that was in April 2021. And by August 2021, China accounts for 40% of the 6G applications already. Okay, so there are some opportunity for us to work on the terahertz research. And the State Key Laboratory of Millimeter Wave partner laboratory in City University of Hong Kong was established in 2008 with the approval of the Ministry of Science and Technology. And our partner is the State Key Laboratory of Millimeter Wave at Southeast University, Nanjing. And here I actually need to acknowledge the support of Professor Hong Wei. Okay? Without his support, we will not be able to establish this partner laboratory. Whoop. In 2010, the Innovation and Technology Commission of the Hong Kong SAR started to fund us at 2 million Hong Kong dollar per year, and with the annual support gradually increases to current 10 million Hong Kong dollar. Now, we will expect that this will be double in the near future. So at the recommendation of our Academic Advisory Committee Chair, Professor Ki Wu, as well as the academician Xing Gang Liu, we started to pursue terahertz research in 2011. And in 2017, we were awarded a 5-year film-based research scheme project. The title of the project is called A Compact System for Terahertz Imaging and Spectroscopy, with key research focuses in terahertz antenna, terahertz generation and detection, and terahertz imaging. Now, in 2018, the laboratory was renamed to State Key Laboratory of Terahertz and Millimeter Waves. Now, our lab has one of the leading team on antenna research, and we have 5 faculty members engaging in antenna research, led by Professor K.M. Lok. And here we have Professor Leung, Professor Steve Wong, and Professor Alex Wong. And Professor Leung was Professor Lok's PhD student at Chinese University of Hong Kong, and Dr. Wong was Professor Lok's student at City University of Hong Kong. Here, what I want to emphasize is that the universities in Hong Kong are actually able to produce world-class researchers, in particular on antenna research. Professor Lok received the 2017 John Krause Antenna Award. And Professor Leung was the editor-in-chief of the IEEE Transactions of Antenna and Publications for 3 years. Now, the magnetoelectric dipole antenna is one of the most important antenna invention in our lab. Okay, and here I would like to emphasize that depending on the frequency, we have to use different fabrication technology as well as different measurement facility to test the antenna that we design. And because of that, the design actually has to depend on the material that we use as well as the facility that are available at hand. So here it is the 1 terahertz ME dipole antenna worked on by Professor Lok and the team here with a very wide bandwidth. Okay, now so we mentioned that terahertz imaging is one of the key research that we have here. So here I would like to show you that we work on the terahertz mirror imaging, and it is what we call the Stokes vector. Basically, the Stokes vector is defined to include the 4 elements, what we call the Stokes parameters, that describe the polarization state of the electromagnetic wave. And here you can see that for different polarization, we have the different Stokes vector. Now, the key thing is that for the mirror matrix, we can relate the incident Stokes vector and the output Stokes vector through this mirror matrix. And this mirror matrix can be cascaded for different components in the system. And eventually, we can extract out the mirror matrix of the device under test. So here are some of the mirror matrix for the, for example, horizontal polarization polarizer, CP, as well as the 45 and negative 45 polarizations. Now, so what we need to do is to have different combinations of measurements of the input polarizations, the incident polarizations, and then receive it with different polarization, so that if we make use of all these 6 polarizations, we have 36 combinations of measurement to do. And from there, we can calculate the mirror matrix elements. Now, here we show you the terahertz mirror matrix measurement. It is a transmission mode. And here is the refraction mode. Okay? Now, here you can see that because we need to focus the incident wave onto the device under test. And these antennas will require of processing different polarizations. So this type of lenses are not available commercially. So we have to design this antenna ourselves. Now, the first antenna that we design, because we need circular polarization, so we basically design a Fresnel zone plate antenna, okay, at 300 gigahertz. This is the conventional design. You can see that they have different rings of this dielectric material to compensate for the phase difference, because we want to have a uniform phase distribution across the aperture. Now, so what we need to do is actually we can have a better compensation of the phase by using this discrete lens. So instead of having a flat lens here, and then they have a different thickness, okay, so compensate for the different phase, basically to compensate the phase for the different path length, okay. So by doing that, because we need to do the circular polarization, so we just follow the approach developed by our colleague Steve, and then we built a polarizer, okay, basically a CP polarizer, okay, and then connect this with our lens, then we can have the CP lens. So basically, by designing this, we can have the X and Y components that have a phase of difference of 90 degrees at 300 gigahertz. So here, the material property, so we make use of an inexpensive 3D printer. Okay, this is only about $5K US dollar. They are not meant for printing lenses at 300 gigahertz. Okay, and so we make use of our time domain spectrometer to extract out the dielectric constant as well as the loss tangents of the material. Now, according to the recommendations of the instruction manuals provided by the company, we are supposed to build our lens like this with the supporting struts here. It turns out that if we do this, the lens will not be uniformly printed. So we have invented an approach, okay, using a very small pillar to support the lens. And after we finish the printing, and we can actually cut out this small pillar there with a brush. Okay, therefore, we can make a lens with very fine detail here that work for 300 gigahertz. Now, in order to test this lens, we have to actually build our testing equipment. Here we have a near field scanner. What we need to do is to basically tailor-make some terahertz pop. Now here we can see that we have a fixture here, which is made by 3D printing. Now, without having this absorbing fixture here, you can see that there are current generated outside the surface of this conducting pop. Okay? And this current will travel down toward the flange here, and it will be reflected. So that will basically deteriorate the performance of the pop. And by adding this 3D printed absorber, you can see that the current basically problem will eliminated. Now, another important feature is we have to make the alignment very precisely. So initially, we'll use the laser to do the alignment, but this is not good enough. So we have to take the phase and measurements of the S21. And of course, if we have a good alignment, then we will have the minimum points of the phase and the maximum points of the amplitude. Okay? And the whole setup is put on a optical table. Now here you can see that by modify the Fresnel plate lens, we can have the measured gain of 27.4 dBIC at 300 GHz. And you can also see that the 3 dB axial ratio bandwidth is 18.8%. Actually, it is bigger than that. As you can see that the 3 dB AR is actually right here, okay? Now, and the measurement and simulation agree very well. Now, it is not quite natural that we will also fill up the region where we have the air, okay? We can also better compensate for the phase difference there. And so this is the discrete dielectric lens that we have developed. And so you can see that by doing so, the gain is increased by 3 dB. So it becomes 30.5 dBICs at 300 GHz. And the 1 dB gain bandwidth is 13.3%. And again, the 3 dB axial ratio bandwidth is larger than 18.8%. Now, the next dielectric lens that we have developed is called the 2D beam scanning terahertz bezel beam launcher. And this basically bezel beam, actually, if you look at the transfer plane of the amplitude, you can see that it has a bezel function type of distributions. And for typical beam, and the beam will diverge, okay? And the bezel beam will actually keep a uniform amplitude along a longitudinal directions for a distance before it diverges, okay? And we can make use of these dimensions, for example, in our imaging systems. Now, there are a traditional approach to develop this bezel beam launcher using these refractive lenses, and they are bulky. And first, it will convert, for example, the point source, the spherical wave, into a plane wave, and then it can change its direction using these prisms and so on. And it is the hexagon lens that will generate the bezel beam. So we can actually combine, use the discrete lens approach that we developed, okay, and then form 4 layers of this discrete lens to achieve it. But nonetheless, it still requires 4 lenses. So what we did is that we actually combine 2 of the lenses and use a single lens, and then we can use 2 lenses and form this beam scanning launcher. And it turns out that the bezel beam direction can be determined by these 2 functions here, and these 2 functions will actually dictated by the lower lens, or in here is the left lens and the right lens. And by using a rotations of these 2 lenses, and we can achieve the beam scanning. Now, to generate, basically fabricate this lens, we develop a pixel element which is in hexagonal shape, and it has a anti-reflection structure here. Basically, is a quarter wave transformer to reduce the reflections between the dielectric and air. So you can see that by changing the length of this part, we can actually have 360-degree phase coverage. And it is the phase distributions of the lens, and it is the fabricated lens. So we can actually stack the 2 lenses together, and then we can fit it by a pyramidal horn here. And then in reality, we can actually use a rotator to control the rotation of these lenses. But for the demonstration, we only have the angle at certain fixed amount. Then we can demonstrate the beam scanning capability. And for the E-plane, and if you can see that the 2 lenses, they can rotate with specific angles, and then we can see this, the beam scan actually from 0 degree to 43 degree here, and it is the some simple calculation, and it is full wave simulation, and it is measurement, and they agree quite well. And it is for the H-plane scanning. Now, comparing to other approaches, for example, this approach using the source at a different location, the field of view is only 17 degrees, whereas by using our approach, the field of view will be increased to 86 degrees. So all the RF modules can be fixed, and then we can have a faster beam steering. Now, we can also develop a 3D focused metal lens. Okay, and here again, we convert the conventional approach into these approaches using two discrete dielectric lenses. And then you can see that by designing the required phase, we can have the electromagnetic field focus at this point. So what we can do actually is through the rotation of these lenses, and we can actually move the focal point along this plane. Okay? And for this approach, we call the single focus method. It turns out when it is steered away from the central axis here, the longitudinal axis here, actually we have the off-axis aberrations. Okay? By modifying the design, that the focal point will be at different locations, and we can actually improve the performance of this lens. And here you can see that by using this multi-focus approach, we can have the beam steer away from the center and with a lower side lobes here. And so you can see that if we rotate the two lenses in the counter directions, so that is one rotate in this direction and the other rotate in the other directions, we can steer the focal point away from the center point. And it is the, you can see that it is a measurement. You can see that the side lobe is better than minus 14 dB. Now, if we have the co-rotation approach, that is rotating the lens, for example, this one is rotate along this direction. This one is also rotate along the counterclockwise directions. We can actually steer the focal point, okay, at the azimuthal angle, as you can see here. All right. So depending on how we rotate the lenses, we can do actually a 2D scanning of the focal point. Now, if we move the separation of the two lenses, we can actually move the focal point, okay, along the longitudinal direction. And therefore, we can have a three-dimensional focal point scanning of this system. Okay, here you can see that it is the simulation result and it is the measured results, so that we can actually have the focal point move along a cylindrical volume. Now, currently, we are collaborating with Professor Ding-Ping Chai and Dr. M.K. Chen for the 3D focusing area beam using the free rotating metal lenses. For our system, we have two rotating lenses, and we have to do a translational, basically, displacement for the third dimension. And in the new design, we need three lenses, and we don't have to move them, we just have to rotate them. Now, one of the approaches of the orbital angular momentum beam is that they will actually diverge as we propagate, okay? And we can actually combine the approach that we have worked on the bezel beam and combine that with the OAM, and then we can generate these non-diffractive OAM beams, okay? And we can also actually choose the range, okay, where these uniform field distributions exist. And by doing so, we can actually increase the signal-to-noise ratios for the receiving antenna and reduce the channel crosstalk. And the key element of this approach is that the field distributions on the aperture here is actually related to the field distribution along the longitudinal direction, okay, through this relationship. So by computing, by designing the range or the performance along this range and coming back to see what kind of aperture field distribution we can provide such a longitudinal distributions, and by doing these approaches back and forth, we can actually design the non-diffractive OAM beam. Okay, here we can see that it is the measured result of the conventional OAM beam that will have a uniform field distributions actually starting from the apertures of the lens. Okay, and this one shows that we can actually choose the range of these uniform distributions. So this is the amplitude, and if we find the phase along this plane, and you can see that this is the L equal to 2 mode of the OAM distributions. Now the other lenses that we have developed is actually the OAM mode reconfigurable lens. Okay, again we have two this DDL, and we rotate them, we design them, and then rotate them, and we can actually generate different OAM mode. Okay, so here are the phase distribution that we have, and we can actually perform some phase swaps because after 360 degree, and we can have we can subtract the 2 pi, and then we can get the phase, and then we can actually modify the phase distribution because it has this even symmetry, and so we can generate the phase distribution of two lenses, and then by controlling basically their orientations, rotations, and then we can generate different OAM modes. Now, after showing you all these lenses that we have developed, and we will move on to other terahertz antenna. In this particular antenna, this is a very wideband antenna. It works from 320 gigahertz to 500 gigahertz using a single layer planar gobble line antenna with end-fire radiation. Basically, we have a quartz substrate with certain thickness and width, and then on top of it, we actually plane the gobble line. And here you can see that if the substrate is very thin at 100 micron, and you can see that the field on the gobble line as well as in the substrate, they have equal amplitude and opposite phase. So they work well as a transmission line, but it doesn't radiate well. But if we increase the thickness of it, the energy will be going into the substrate, and then eventually it will radiate. So we also try to see the different shapes of this substrate at the end here, and we can find that the rectangular approach actually have a better performance in terms of the gain, but the gain actually dropped by about 2 dB as the frequency increased. Now, taking advantage of a power divider using the gobble line, we can actually manipulate the field distribution in the substrate. And here we can see that when we properly design the antenna here, you can see that at 350 gigahertz, and the wave will propagate along the line as well and on the substrate, and eventually it will radiate, and it works quite well up to 300 gigahertz. And the gain will actually increase by 2 dB as opposed to using a single line. And here you can see that the efficiency of this antenna is actually all above 80% with the peak value at 88% of the efficiency. Now this is the performance. It is a very wide band, and the gain is from 8.5 to 11.3 dBi, and the thickness of the substrate is about 0.4 wavelength. And then you can see that it is a radiation pattern, and in fact it is quite stable across a very wide frequency. And this coplanar waveguide fed structure and can be easily integrated with other photonic devices. Now this is another high gain terahertz folded reflected array antenna that we have developed, And basically, we have two meta surfaces here. One is at the bottom. It is a meta surface, and then we have basically a two-layer polarizers here. Okay, so we have an isotropic element here. So it will have decomposed into two components, and one component will go through, and the other component will be reflected, and eventually the polarization will be changed by this bottom meta surface. Eventually, they will be radiated in the forward directions. Now, the key approach of this antenna is our fabrication capability, and with the help of Professor Sarah Pang, and we can use the reactive ion etching to generate this, to fabricate these very fine features of the bottom meta surfaces. Okay. So this is the testing setup, and it is the fabricated antennas. So you can see that it is the reflection coefficients, and it is the antenna gain. And here you can see that the radiation pattern, when compared with simulation, they agree very well, and it works from 1 terahertz to 1.8 terahertz for the E plane as well as the H plane. And the gain is 33.7 dBi, and the 3 dB gain bandwidth is 7%. Now, here I'm going to introduce something very interesting that we have developed, and it is called the amplitude modulated liquid wave antennas. So in the AM modulations, you can see that we have a carrier wave here, and in a time domain, and it is the modulated sinusoidal modulated signals, and it is the modulated waveform in the amplitude modulated radio. And in our design, for the AM radio is in time, and we do it in the spatial domain. So this is the modulating wave. Now you can see that it is in X, okay? And it is basically the periodicity of these modulations. And it is for the carrier wave, and it is the modulated wave. Again, it is the variations along the X direction, along the length of the antenna. Now, so you can see that basically we follow the distributions of these modulations in space, and we use the corrugated guide here to mimic the modulated signal. And by doing so, we can feed this antenna with a waveguide fit here. And then this liquid wave antenna will radiate, and you can see that the beam is actually radiated in these particular directions. So this is the fabricated antenna. Now, in fact, the modulation doesn't have to be sinusoidal. And in fact, in this particular example, we demonstrated a flat top radiation pattern. So this is the basically the spectrum of the desired radiation pattern. And so you can see that the spectrum of the unmodulated carrier wave is actually outside the visible regions. And if we look at the spectrums of the modulated wave, these portions of the wave is actually within the visible region, so they will be basically radiated. And so therefore, it is the distributions of the spatial form of the waveguide, and then you can see that we change the width of this corrugated waveguide according to this modulating wave, and it is the simulated and measured results, and they compare quite well. And the antenna that we have demonstrated earlier is a millimeter wave, and in fact, we can extend the approach to develop a terahertz guided wave driven meta surface antenna. So you can see that by having this spatial modulation here, we can also have the beam directed at a certain direction, and when we change the frequency, you can see that the beam actually basically steer toward different directions. So this approach, we have this silicon-based meta surface antenna, and it is fully compatible with the CMOS technologies and the integrated photonic technologies. And it's highly efficient because the material that we use is high resistivity silicons. And in particular, this type of antenna can be used, again, for the data center. Now, in collaborations with Professor Trader Jones and his group, basically, Dr. Dai actually spent 2 years here with our group, and he worked together with the Gangbo Hu, and we developed this space-time coding meta surface antenna. So this antenna at this point is at a millimeter wave. You can see that we can actually control the output beam in terms of the directions as well as their frequencies by using this 1-bit on and off switches, okay, placing it along the antenna structures. And it can be extended to on-chip integrations, and you can do the harmonic independent control of it. So here we just submitted the paper, so I would not be able to share with you all the detail, but I want to show you some of the interesting results. And here you can see that by doing a signaling using the FPGA, by controlling the switches with the on and off sequences, and we can direct the beam to a certain direction, and we can also control its harmonics. So here is along the directions of the antenna here, and this number, and this number is the time sequences of our control, and the color represent 1, that means the device is on, 0, that means the device is off at certain time instance. By doing that, and we can see that it is the power spectrum for this harmonics, and then it turns out the beam is actually pointing at these directions. Now, if we change the this on and off sequences, okay, as well as the on and off along the axis of the antenna, so you can see that we can actually change the beam directions, okay, at different angles. Okay, now we can also change basically the periodicity of these modulations here. So this is the spatial periodicity, 6.9 mm and up to 21.6 mm. So you can see that they could have, with a different periodicity here, they can generate the beams, okay, at a different directions. And at this point, all the M number here are all 0, but they can, the beam can be steered toward different directions. Whereas if you use a different control sequences, the beam direction can be different, and the radiated harmonics can also be different. So in this particular case, and we get M equal to -1, +2, and +3, and they can be point toward 3 different directions, or they can be point at the same directions. Okay, so by simply controlling the on and off of the switches, okay, and in terms of time and in terms of space, we can change the performance of this leaky wave antenna. Now, after that, we are going to move on to the on-chip antennas, because we need to develop basically sources for the terahertz, okay, in 2 different approaches. One is from the IC approach, the other one is from the photoconductive antennas. So here we work on the on-chip antenna. Now, in the past, when people work on on-chip antenna, they basically try to show off the effect of the silicon here, okay, and this is what they usually do. And what we found out is that we can also make use of the silicon substrate, and by making use of its volume here, we can actually enhance the bandwidth of the antenna as well as its gain. So we designed this antenna with a conventional rather approaches of the fitting the dielectric resonator. So it's called a chip integrated dielectric resonator antenna. So you can see that the antenna, okay, because of the different modes, we can actually enhance the bandwidth of the antenna. So this is the measurement setup that we have developed. So you can see that we have the capability of measuring, characterize the chip antenna, okay, as well as measure its radiation pattern. Of course, because we use a pop fit here, we can only measure the H-plane of the antenna. So here you can see that this is the impedance bandwidth of the antenna. So for the simulated impedance bandwidth, it is actually much wider than our measured one, because actually it is at the edge of the frequency extender. So therefore, it may not be as accurate, okay? And it is so the gain, and the gain of the antenna is actually maybe on the average is 7 dBi. Now this is the radiation pattern, the simulated one as well as the measured one, and it agreed quite well from 250 gigahertz all the way to 322 gigahertz. Now we need to actually steer the beam. Okay, we have developed an on-chip beam steering terrace devices, and that we can have basically a low millimeter wave signal here, and then we can do a tripler and then a quadrupler, so that the frequency can be expanded to 320 gigahertz. And here we have 4 elements here. By controlling their phase, we can actually point the beam to different directions from minus 30 degrees all the way to positive 30 degrees. Now because we need high power source for our imaging, so we developed the scalable radiator ICs, okay, at terahertz frequencies, using basically the up conversion approach. And that it is the one of the IC that we have developed, a 2x2 array using the microstrip patch antenna. So the frequency operate at 482 gigahertz, and then it is the radiation pattern, and the field actually radiating upward, and it is the directivity of the antenna array, and it is about 10.5 dBi, and that the output power is actually about 162 microwatt. Now, we actually increase the size of this array with different approaches. For example, we developed a 4x4 slot antenna array. So the antenna radiation is pointing downward. And by incorporating this chip with an inexpensive elliptical Teflon lens, we are able to achieve about 30 dBm the EIRP, and this is the largest that it has been reported for this scalable radiator IC. And it is actually just published in February this year. Now, this is a second harmonic approach. Now, in this IC, we use a third harmonic. Actually, is a 4x8 array, and that we were able to achieve about a -3 dBm output power, and this actually is the highest among all the IC, scalable IC, go beyond 600 gigahertz. So we can also again use a Teflon lens here. The EIRP actually is about 27 or 28 dBm. So here is our testing setup. So we can actually build our testing setup here, and we can compare that with the Fish equations. So we know where is the far field range of the antenna. So this is measured at the far field, and this is the inexpensive Teflon elliptical lens, the EIRP, then we can measure. And this is another approach that we have. Now, this one actually makes use of a miniaturized patch antenna. So the antenna, the radius is actually upward again, and we were able to have about a minus 22.8 dBm output at 472 gigahertz. So the frequency tuning range of this antenna, this IC is 4.2%. And again, with a low-cost Teflon lens, the EIRP is about 30 dBm. Okay, and all these IC can be used as a source for the terahertz antenna that we have shown you before, and they can also be used for the terahertz imaging. Now we go back to the imaging, and here is our mirror matrix imaging at 300 gigahertz, and it is for the transmission mode. So you can see that we image this part of the leaf, and then you can see the different part of the leaf. And if you look at this diagonal part, they all look pretty much the same. This is with the different polarization images before we compute the mirror matrix. And for the leaves, even the conventional approach looks quite good. Whereas for the refraction mode, so this is the target that we have, and some of the width of these lines are actually below one wavelength. So you can see that for the polarization images, they all cannot see all this line. Whereas for the mirror matrix imaging, and some of the feature, okay, can be better. For example, like this one, okay. But if we further decompose this mirror matrix, okay, we can enhance its the image quality too. So in particular, this is what we call the linear retardance, and you can see that we can identify these different strips better. This is actually sub-wavelength, so it's hard to image this well. Now that is an index called the SSIM. It's an indicator how good your image is, and so in a way for the leaves, okay, these are the better one, okay, without the decomposition of the mirror matrix, and it is 1, and then all the rest are actually less than 1. So whereas for the refractive mode, you can see that this particular image has the best SSIM, and that all the rest are not as good. So you can see that different reconstructions have different indices, and this is the best image that we have. Now we can also do the image in time domain. So you can see that because we make use of our time domain system, we actually have both the amplitude and phase information. Okay. In fact, we can actually construct the other polarization through the measurements of these 4 combinations. Okay, the positive 45 degree and the negative 45 degree. So here is the polarizer that we have developed so that we can control the polarization to positive 45 and negative 45. So these are the images that we can see. If we look at one of the particular calculations that by attenuation, you can see that is a very good contrast of the wing of the leaf and the remaining part of the leaf. So the image of the leaves, okay, can be actually enhanced. And this is visually we observe, but you can see that actually through this imaging, we can see the details of the leaf. And through the reconstructions of the third dimension in time, we can actually strip the layers of the leaves. Okay, so you can see that at different time, we are actually seeing the different layers of the leaves. And this is the 3D constructions of the image of the leaves, okay, with the third dimension in time. And this is, I guess, it is an interesting animation to show. Basically, the actual imaging of a fish, of a zebrafish, provided by Professor Zhang here. And we can actually see that at low frequency, we don't recognize the fish. As the frequency increases, then you can see that the different part of the zebrafish. Okay, so this is the, we also try to improve the output power of our time domain spectrometer. So here you can see that it is the where the photoconductive antenna is located. So we have developed our own photoconductive antenna and put it into the module here, and we can do the testing. So without giving you the detail, we make use of the graphene, and we can see that by comparing with the graphene and without the graphene, we can see that using the bow tie element with a very narrow gap, we can actually increase the radiated power by 5. Basically here, you can see that this by 5 dB here with the intensity here. And if we make use of the nanowire, semiconductor nanowire, again, we can improve the performance of our output, even if we use very inexpensive substrate. So where do we go from here? We have developed terahertz sources using both the up conversion techniques as well as the down conversion technique, basically the photoconductive antennas. And we have developed a wide range of terahertz antennas. Okay? And they could be used as a source for the antenna that we have developed at the IC. Okay? And they can also be used for the terahertz imaging. So we are currently working on the IC implementation of our beam steering devices, and based on the space-time coding metasurfaces. So we can increase the frequency as well as reduce the size. And we also plan to incorporate baseband signaling into our terahertz IC for 6G with our sister institutions. So in summary, while the 5G spectrum has not been fully utilized, but we are already working on radio frequency front ends for 6G. And we have to look for alternative design, okay, fabrication processes, as well as the different materials and testing approach that are needed. Okay? And the fabrication processes and novel materials are basically essential for successful development of these devices. And of course, low cost and high power terahertz sources are required. And our lab has the state-of-the-art millimeter wave and terahertz measurement facilities, and our investigation informs us the deficiencies of our current practices. So we hope to conduct more innovative terahertz research and preparing ourselves for the 6G. And here, I would like to acknowledge the support of our funding agencies and the collaborators on the terahertz research, both at CDU and outside CDUs, and these are in the mainland. Okay, and here are some of the team members contributing to the terahertz research. Some are postdocs and some are graduate students. And this is the photos of our postdoctoral researchers and PhD students in my group. And that was not the most current one. That was shot at June 8, 2021. So a couple of the members have left, and we also have some new members joining our team. And with that, thank you for your attention.
Thank you, Professor Chan, for a very informative and excellent talk. So now we have the Q&A session. I have found some questions from the audience here. So let me read them out one by one first. The first question is by Mr. Tilon. He asked why the CP antenna was made with a 5K 3D printer instead of using nano fabrication. So, Professor Chan, can you answer this question first?
Well, we try to use a very inexpensive approach. And we found out that this 3D printer, although it's not expensive, but the resolution is actually quite good. As we have pointed out, the laser spot size is 140 micron. The layer size is 25 micron. So we were able to make those lens, okay, and it works well. So that's why we do not resort to use very expensive, basically nano fabrications. But on the other hand, if we want to increase the frequency further, it would not work. So that's why we have to resort to the nano fabrication in collaboration with Professor Stella Pang, as we have demonstrated on these 1 terahertz antennas, whether using this folded reflector array or the guided wave-driven antenna. So it is out of Now, one more important factor is that we can do the 3D printing within a day. But if we use nanofabrication, it will take a lot of time and a lot of experience in order to do it well.
Okay, the second question is what type of dielectric materials are used in these devices?
Now, we actually, as I have shown you earlier, that we have two types. If we do 3D printing, this is the resin provided by the company. It's called the high temperature resin. And again, it is not very expensive. Whereas for the 1 terahertz antenna, we have to use this high resistivity silicon. Now, how expensive it is, actually, I do not know. Because so far, Professor Stellapan have not sent me any bill for buying the substrate. So she's very kind. But they are very common material, put it this way.
Okay. Another audience want to ask, while researchers see great potential with a high-frequency version of 5G, it comes with a key challenge. It is very short-range. Objects such as trees, buildings cause significant signal obstruction, necessitating numerous cell towers to avoid signal path loss. How can this be improved? You want to ask?
Well, I guess this is the reason why people want to use this integration system of the air, space, sea, and ground. So, for example, if you want to have satellite communications in space, terahertz is okay. That is no absorption due to air, right? So, on the other hand, the research done by basically the NYU Wireless Center group there, they demonstrate that even at over 100 gigahertz, the attenuation loss is actually affordable in the sense that if we have high gain antenna as well as high output power of the systems. So in a way, we are working on the different technology. Hopefully, we can actually improve the status of this technology in preparing for the future 6G. We still have maybe 8-year time, okay, before it is deployed. So we need to work hard, okay, in order to catch up. Yeah, that is a lot of challenges, but we cannot say that because there's so many challenges, we will not work on it. So in fact, because it's so challenging, we may have produce some good impact research output if we are fortunate or we work hard enough. This is my answer to it.
Yeah. One audience said, thank you very much for Professor Chan's excellent talk. Many attractive and interesting words in this talk. Will Professor Chan give some comments on main challenge for device designs in terahertz application? Is the material characteristic one of the issue for the design?
You mean for the chip implementation or other approaches?
I guess he's talking about the not only the chip, because he's talking about the material characteristic.
Okay.
Maybe the material for the antenna, also for the IC board.
Okay. Okay.
I guess in general.
Yeah. Okay. Now for let's say, let me try. Now, for example, for this terahertz guided wave driven matter surface antenna, the loss is not significant. Okay, and so this is not a big issue if we can make use of this material. But sometimes we cannot. Now, we show you that the lenses that we develop using the 3D printing, the loss is actually not too small, 0.03 loss tangent. So when we increase the frequency, even if we have a better 3D printer, if we use the same material, the loss may be a factor. Okay, so we need to use basically a low loss material. On the other hand, for the Teflon lens that I have shown you, the loss is actually very small. So even for 700 gigahertz, we were still able to have a very high output. The loss is not significant. So depending on the frequency and depending on the material that we choose, and in particular the application scenario, I think that is the key part.
Okay. Professor Chi-Ling Chen, I want to ask, dear Professor Chen, thank you very much for your excellent sharing. Could you please comment on what will be the killer applications of terahertz systems in 6G networks? Thanks, Chi-Ling from Singapore.
Yeah, thank you, Chi-Ling. And I think this killer application, everybody want to know. And I also want to know. But there's a lot of people who are talking about this holographic telepresence. Now, I think it is maybe possible. The reason is this. In the old days, when we have a teleconference, we only have the audio. How could we imagine that in this pandemic era, we're able to use Zoom, that we can see each other, we can actually watch if we need the video and so on, we can communicate with each other quite well. So I think if we work hard enough, maybe telepresence is possible. I think people are already using this so-called digital twin, for example, to do remote control of certain equipments. Okay, and for example, the tele-Chinese medicine is already in use. People can consult it through the internet. But on the other hand, they cannot feel the pulse of the patients because there is no sensing capability at this point. But this is one of the key features of the 6G. So I think this tactile sensing would be another killer application. It will basically facilitate the telemedicine greatly.
Okay. Let's see. Professor Stella Pan. Professor Stella Pan, you have a question?
Yes. Thank you, Professor Luke. Professor Chen,
Can you turn on your video? Can you turn on your video?
I did already.
Okay.
I did.
You did.
No, it doesn't work. It doesn't matter. I can just talk.
Okay. It's okay now. Yeah. Good.
Thank you, Professor Chen. You gave an excellent talk and covering a lot of different materials, and this is very fascinating. We talked about this before. I think one of the key things that one would like to see is to have extensive integration, right? Yes. Integrating multiple elements, passive, active devices on the same chip, and providing a lot more functions, right? Making the chip a lot more functional. Why are we not seeing as much of this huge, much larger integrations with various devices that we can get all put together on the same platform?
Yeah, I think actually they are. But for example, at lower frequency, people actually have to work, what they already work together. Otherwise, we will not have the ICs for the 3G, 4G, or 5Gs. But in the future for 6G, it's difficult to basically master all the different techniques in one particular group, for example. And it takes some time to talk to each other, okay, even within our own lab. Okay, it takes some time to actually learn other people's expertise as well as how they do different devices and so on. I think it's gradually happening. So for example, within our Sticky lab, we work with different people. I work with you, and you help us to do the fabrications. Without your help, we will not be able to make a terahertz antenna. So we will still be working on only up to 300 gigahertz. Now, on the other hand, we can generate this RFIC or terahertz IC, but we don't have the signaling part. And at this point, I'm working with other our sister institution, and because we have submitted some proposal and it has not been, we do not know the result yet, so I don't want to expose the detail, but we have to work with different parties. So in a way, it's up to the point that we cannot just close our door and work within our own lab or own room. We have to go out and collaborate with other people. For example, the work that we work on this signaling of this liquid wave antenna with the Professor Cui Taijun's group, it turns out that they are very good on this signaling. So we have to work together and to demonstrate that the idea work. So I guess if we can have more collaborations, then we will have the opportunity to basically achieve bigger impact and more output. So I think it is unlike in the past that we can close our door, write our own program, and work on the paper. And this is what I was doing when I was a graduate student, that we do computational electromagnetic, all we need is a computer. I cannot say that all we need is papers and a pencil. Those are for mathematicians. We need computer too. But now we have to do simulation, modeling, hardware, and testing in order to achieve something. So I think this is an opportunity for us to work together to create bigger impact research. Thank you for your questions.
Totally agree. Yeah, thank you, Professor Chen.
Thank you.
Okay, thank you, Stella.
Thank you.
We have many questions here. Now, another question is from Dr. Jinong Ying from Sony. Thank you for the informative talk. What is your view of terahertz technology in 6G application cases, point-to-point, mobile case, or mainly in sensing? What are the main challenges?
Okay, now I guess sensing would be important because we have also show you some imaging type of research. Now I guess it is no doubt that we can actually do near field. For example, we can, for example, on this, we have a lot of monitor here, and they can actually provide the wireless link at a very high speed, okay, for 6G. For example, we can download for a near field proximity couple approach, we can actually download I was told that all these Marvel movies in only like tens of seconds, all the movies, not just one, okay? But in terms of long range, I think it is quite challenging because of the atmospheric absorptions. So then you need more cells. But on the other hand, the work from the NYU have also claimed that well, at least it's feasible, but we need a probably high power facility. So it may not be best for mobile. Mobile may be still lower speed, but when we have a HKIAS, for example, that can generate enough power to generate this 6G signal, and we can put our mobile phone close by, we can get all the information much faster than the 5G. I think that is some of the approaches that can be done. But not only that, we need the hardware part, we actually also need the computation part if we want to have the applications for mobile. For example, how do we generate these virtual images or holographic images? It needs a lot of basically computation, okay? Maybe, so in a way that we also need very fast algorithm. That is the reason why we work with other group, in particular from the University of Hong Kong, who are actually quite good in certain of these wireless communication approaches, so that our goal is to have faster computation and how it can integrate with our RF devices.
Okay, actually, Dr. Ying also want to ask, what is your view of control channels by using intelligent services in terahertz band?
Well, I think it's coming. We are working on it. In fact, we have demonstrated it at a lower frequency, a millimeter wave. And in fact, we are going to go to the higher frequency using the on-chip implementation. I think the signaling part may be okay, I think. All right, this is what we hope for. Otherwise, when we fabricate all the IC and do the testing and find out the signaling part is too slow, then we are in trouble. I think I have the gut feeling that it will work. Okay, I do research by gut feeling. So sometimes, of course, my head is bang on the wall, but most of the time it's okay if we work hard enough. So the key is to have hardworking graduate students and very talented graduate students.
Professor Kiwu also has some question for you. Hi, Chi. A great talk with many interesting ideas and demonstrations. have you considered 3.5 or other ICs technologies for your terahertz systems?
I guess eventually we need to, okay? Because the power, in fact, is the problem, okay? And we also need other technology because the phase noise right now we still have to improve it for our devices. And unfortunately, I'm not a basically material science people, although some of our lab members are. So I guess we just have to talk more often with them to learn more about these V5 compounds. And in fact, we have a lot of material scientists at CTU. And if they are willing to work with us, I think we can make some achievement there along that line. Okay. I want to emphasize that, Key, remember that we are all both trained as a computational EM guy. And Professor Ki Wu actually gradually developed to branch out to many different aspects of the applied electromagnetics. And I am stuck with the computational EM, but after a long time, I actually also losing the edge in computational EM. So now I rely on my graduate student and postdoc to work on the antenna and devices. So my only contribution is to be their cheerleaders, as I always claim. They have to be actually working very independently. Fortunately, they are all very talented. So I was able to show you a lot of different results today. Actually, not because of me, it's all because of their hard work and innovation.
Actually, Professor Wu also want to ask, can you elaborate more about your non-diffractive transmission techniques, which seem to be of significant interest? Thanks a lot.
Oh, okay. Actually, it was reported in a paper already. So let me see if I can find that page. We can, Key, you can refer to the paper that was published. Let me see. See if I can find. No. Oh, maybe I pass it. Oh, right here. So this was reported in June 2020 is the IEEE TAP. Okay, so basically, when we develop this approach, it is basically uses so-called the hexagon lens. People have done it before. It's not that we develop it anew, but we just have a different implementation. Basically, all you need to do is to look for the phase distributions. Okay, that will generate these kinds of non-diffractive beam. So we just have to design a pixel element that can correct the phase distributions. Okay, then we can make those non-diffractive beam. Of course, at tera frequency, that range is not too long. Maybe 40 wavelengths, so which is only, say, at 300 gigahertz, maybe only 40 mm. But at lower frequency, we can extend the range. Or you can make the antenna bigger, of course, then you can extend the range. Yeah. There's a lot of mathematics there. That's the reason why I skip it, because it would take an hour in order to go through all the detail in terms of mathematics. And my excellent graduate student, Dr. Gangbo Wu, and he developed all these derivations. And actually, it's very nice work that he did.
Okay, Professor Wang Hongjian want to ask you a question. Can you ask a question? Oh, maybe some problem. But anyway, let me ask the questions from, we have many more questions actually. One question is the envision future network flexibility along with the contrastive requirement. of 6G services and applications, he supports a complex interplay between large-scale ecosystem of software and hardware network components, rendering classical theoretical approaches unable to seamlessly scale to the massive problem size. What are the potentials of AI in elevating this problem? So I think that the question is whether you think AI can help us to solve the problem in the 6G services.
Well, I think AI certainly would help. Personally, I did not work on AI, but many of my colleagues, because recently I reviewed the students' work, okay, under different colleagues. At least 3 of them, okay, 3 of my colleagues, I don't want to mention it. They all want to use, they are students, all want to use AI to design new antennas. And I think it's basically a optimization technique, and we have benefited in the past to use different type of optimization technique to enhance the performance of our antenna, for example. So from that experience, I think it will help definitely. Okay.
Okay. Mr. Ma, I want to ask, thanks a lot for Professor Chan's lecture. It is very interesting and inspiring for me. I have a question that it seems that the current 6G studies are more focusing on laboratory studies. How far away are we from the commercialization of 6G?
Oh, this is a very good question. That's why I put up the title, Are We Ready? Actually, I think we will all work on it. I don't think we are really ready yet, of course. Right? Through my talk, you can sense that. I think now, even for this big company who put in a lot of investment, like Huawei, Samsung, LG, and they have demonstrated, at least for that I can find on the internet, LG and Samsung, they have demonstrated some of these 6G capability. You can see that they all work with this research group. Some with those in the US, in France, or in Germany. These are all laboratory research. But on the other hand, the professors do not have the resources to actually do the real demonstration sometimes. So I guess once we can do the demonstration, there's still a long way to go to cut down the cost in order to make it to let it go to the market. So a lot of this demonstration that they have demonstrated require a lot of big desktop equipment and so on. Right? And how can you shrink down everything into a mobile phone? I think we still have a long way to go. Luckily, we still have maybe another 8 to 10 years before the real deployment of 6G, and hopefully we can improve the situations. So the key thing is, how do we basically put everything together and shrink down the size? And on the other hand, we also want to make the device low power. Otherwise, we cannot use it for real applications in a mobile communication arena.
One other question is, what is the advantage of terahertz imaging against X-ray or MRI?
It is at different scale. They are complementary. They are not exclusive. For example, X-ray is actually maybe have health issues. Terahertz is non-ionizing, and the power is much lower, and it can, in fact, it cannot go through my hand, right? It can actually go through the surface of my hand. It's easy. If it can actually have enough power to go through my hand, then it may cause certain health issues. So it depends on the applications, okay, what we are trying to look for. But on the other hand, because the terahertz has a lot of absorption through water, for example. If you have biological tissues, they have different water content, and you can actually have a bigger contrast among the different parts of the sample that you want to image. And that's also the reason.
Okay.
Yeah. also the reason why we want to, for example, produce higher power. In fact, some of our IC have higher output power than our measurement facility, so that our imaging can be improved.
One more related question is, terahertz wave have huge loss in air. How do we use it in our common life?
Well, it depends on the frequency. They have certain window, as we have shown you, that the absorption will be lower. Okay. Now you can see that. Of course, we do not intend to use it for long-range communications. But on the other hand, in our measurement facility that we show you, a meter or two is okay. In the past, when we say that we have the equipment and we can do the measurement within like 2 meters, there are some Russian visitors in our lab. They came that, oh, it is impossible. That means that you don't have enough power. But now we can actually do that with our own IC source. So it takes time to make progress. Okay. Now, on the other hand, for generations of the terahertz, it can have big power if we use vacuum tube, traveling wave vacuum tube, for example. And there are many people working on that.
I think time is up now, and actually we have many questions being asked. So for those we cannot answer, Professor Chen do not have the time to answer at the moment, you can contact us for future sharing. And I'm also apologize. Some audience actually want to raise hand, but somehow they cannot ask question due to some of the problem using the software. But anyway, thank you, Professor Chen, for a very excellent talk. And I do believe that terahertz technology has a great future. So before the end of our talk, Professor Chen, do you want to say a few more things before we end this talk?
Well, of course, I would like to thank all the audience. As a matter of fact, many our good friends are attending this lecture, and I thank them for their support for all those years. And I would like to thank the funding agency in particular, and CTU. Without their support, some of the research we will not be able to do. And once again, we have excellent measurement facility funded by the government and the university. And we also have a lot of opportunity if the government indeed double our resources. So I've been talking to our colleague to ask them to step up their equipment, the recruitment of maybe postdocs or graduate students, so that we can produce more meaningful and useful research. And once again, I would like to thank all the audience, good friends, and thank you for your support and your patience to go through this an hour-long lecture. And I thank you very much.
Okay, thank you all. I hope to see you all in future conferences or other occasions. Thank you again. Goodbye.
Thank you, Professor Lok. Thank you. Goodbye. Thank you.
Bye.
Bye-bye.